Hello everyone, welcome back to Sai Tutorials Jamkandi. So in our tutorial, 10th class Kannada medium, English medium, Math, Science, English, as well as 8th, 9th class English medium, Kannada medium, Math, Science, English classes are available in the regular classes as well as in the online classes. So please don't forget to subscribe our channel, and also you can join and learn the concepts. So dear students, in the previous session we have discussed some concepts related to your physics second PUC chapters, that is second chapter. Now, in the yesterday's class, I mean in the previous session, we have discussed some of the concepts related to your syllabus, that is electric potential at a point due to a short dipole, and we have derived an expression, that is V is equal to Q into 2A into cos theta divided by 4 pi r square is equal to P bar dot R bar divided by 4 pi epsilon naught into R square, where P is equal to electric dipole moment. And some of the concepts, that is some of the cases where we derive the dipole on the axial line and the equatorial line and for a and some another concept, that is for continuous distribution of charges, that is V is equal to line integral of d capital Q divided by 4 pi epsilon naught into R, where dq for the line linear distribution of charge, for surface distribution of charge, and for volume distribution of charge. Okay. So in today's session, let us discuss about equipotential surface. It's a very important concept related to your syllabus. Equipotential surface. Okay. So what do you mean by equipotential surface? First and foremost important thing is, what is equipotential surface? An equipotential surface, just a second. Okay. Okay. Definition. This is definition actually. An equipotential surface is a surface passing through points at the same electric potential. At the same electric potential. So, what do you mean by equipotential surface in the sense? An equipotential surface is a surface passing through the points at the same electric potential. So, whatever the object or whatever the surfaces are there, no? So, is a surface passing through the points at the same electric field. Okay, it is having the same electric field over all the surface, or else the locus of all the points which have the same electric potential is called as equipotential surface. Okay, it is having the same points, passing through the points at the same electric potential, or the locus of all the points which have the same electric potential. This must be noted. Same electric potential must be noted. So those surfaces are called as equipotential surfaces. There are some of the important properties related to the concept. First and foremost important, that is equipotential surfaces around a point charge are concentric spherical sphere. So at any point on the equatorial surface, okay, the component of electric field along the equipotential. See, equipotential surface around a point charge are concentric spheres. This must be noted. So whatever the surfaces that is related to equipotential surfaces around a point charge, okay, around a point charge are concentric spherical surfaces. Okay, those surfaces are called concentric spherical surfaces. What do you mean by concentric? See, every surfaces have a point or origin inside it. Okay, am I right or not? So this surface is concentrating towards, I mean, this is all due to the that centered, I mean concentrated concentrated origin. Okay, so equipotential surfaces are around a point charge are concentric spherical spheres. This is the first and foremost important thing or property. Now Equipotential surfaces around a charged cylinder or a line of a charge are concentric cylindrical surfaces. The name itself, the name itself. Suppose equipotential surfaces around a charged cylinder. If you consider the charged cylinder, okay. If you consider a cylinder, just a second. Let us consider a cylinder. Now, equipotential surfaces around a charged cylinder. Okay, around a charged cylinder or a line of charge are concentric cylindrical surfaces. See, whatever the surface is there, no, that in that position only the charges are distributed. Am I right or not? See, equipotential surfaces around a charged cylinder or a line of charge are concentric cylindrical surfaces. Okay, are concentric cylindrical surfaces. This is the second point. Okay. Third important point. See, equipotential surfaces due to a large charged plane are planes parallel to the surface. See, equipotential surfaces due to a large charged plane. Okay. Just a second. Okay, let me come back. Equipotential surfaces due to a large charged plane. Okay, large charged planes are planes parallel to the surface. If the surfaces are parallel, if the surfaces are plane, I mean, if the surface is plane like this. Okay, see, it is a plane sheet. Let us consider it plane surface. Am I right or not? It is a plane surfaces. Say equipotential surfaces due to a large charged plane. It is a plane. This is a plane. So the planes are parallel to the surface like this. Parallel to the surface. Okay. Or you can also consider like this. Suppose these are the two plane sheets. The planes, okay, the planes are parallel to these sheets like this. If you consider any equipotential surfaces due to a large charged planes, if you consider the planes are planes parallel to the surfaces. This is another property. I hope this concept is clear to you. So next and foremost important, that is for a uniform spherical distribution of charges, for a uniform spherical distribution of charges like a spherical shell or a sphere, the equipotential outside the spheres are concentric spheres around the center of distribution of charges. This is very important. See, for a uniform spherical distribution of charges, if you consider uniform spherical distribution of charges, if you consider a spherical distribution of charges like a spherical shell, just a second. If you consider a spherical shell, okay, or a sphere, the equipotential outside the spheres, whatever the surfaces, the equipotential outside the spheres are concentric spheres around the center of distribution of charges. See, if you consider a spherical shell or a spherical distribution of charges, the equipotential outside the spheres, okay, whatever the outer surface is there, no, the equipotential outside the spheres concentric spheres are concentric spheres around the center of distribution of charges, okay, around the center of. I have told you already, concentric means the surface is balancing towards the center. It is having some kind of origin, so the surface, the whole outside the surface is balancing towards the origin. So the equipotential outside the spheres are concentric spheres around the center of distribution of charges. So for a uniform spherical distribution of charges, like a spherical shell or a sphere, the equipotential outside the sphere are concentric spheres around the center of distribution of charges. As I have told you in the first property, that is equipotential surfaces around a point charge are concentric spherical surfaces. Okay, equipotential surfaces around a point charge are concentric spherical surfaces. So if you consider the spherical shell or a sphere, the linear or the spherical distribution of charges, that is the equipotential outside the spheres are concentric spheres around the center of distribution of charges. See how charges are distributed around the center, I mean concentric circle, whatever the circle, the surface is there, no, so in that condition only the charges are distributed. So then equipotential must be outside the surfaces are concentric spheres around the center of distribution of charges. How the surface is there, no, in that condition only the equipotential also applied. Now all the lines in a plane passing through the center of a dipole and perpendicular to the axis of the dipole lie on an equipotential surface of zero potential. If the dipole lies along the x-axis, the yz plane, that is x is equal to 0, is an equipotential surface with uh, potential v is equal to 0. See, let me consider. All the lines, okay, whatever the lines in a plane passing through the center of dipole, okay, passing through the center of dipole and perpendicular to the axis of dipole. See, if you consider the plane, okay, if you consider the plane, all the lines, see, all the lines passing through the center of the dipole and perpendicular. See, if the planes are parallel, then if the this is the center of the plane, okay, center of a dipole and perpendicular to the axis of the dipole. See, I have told you in the dipole that perpendicular axis like this, perpendicular axis of the dipole lie on the equipotential surface of. See, if the perpendicular axis is there, then the equipotential surface of a zero potential, then there will be a potential will be zero. So if the potential lies along the axis, the yz plane, that is x is equal to 0. If you consider the yz plane, suppose this is x axis and this is y axis and this is z axis. So all the lines in a plane passing through the center of dipole and perpendicular to the axis of the dipole lie on an equipotential surface of zero potential. See, if the dipole lies along the x-axis, if the dipole lies along the x-axis, then yz plane, there is no any, I mean, the physical meaning at y and z axis. So in that condition, is an equipotential surface with a potential V is equal to 0. So if the dipole lies along the x-axis, then the physical significance of y and z axis will be 0. Then potential will also be 0. So all the lines in a plane passing through the center of the dipole and perpendicular to the axis of the dipole lie on the equipotential surface will be 0. Why? Because if you cut the dipole will be in the one direction, okay, the other direction must be 0. Okay, the YZ plane will be 0 is an equipotential surface with a V. Potential V must be 0. In that condition, the potential will be 0 when it is perpendicular to the axis. Okay, when it will be perpendicular to the axis. So in a case of uniform electric field, equipotential surfaces are planes. In case of point charges, equipotential surfaces are concentric spiracles. On see, if the electric field lines are always perpendicular to the equipotential surface, electric field intensity will always be perpendicular to the equipotential surface. See, I have told you that if the equipotential surfaces, the dipole and perpendicular to the axis, whatever the lines are passing through the center of the dipole and which are perpendicular to the axis of the dipole, then the potential will be 0. Then intensity will also be perpendicular to that equipotential surface. Okay, the whatever the electric field intensity that passing through the plane is there, no, though, so that electric field intensity is always perpendicular to the equipotential surfaces. Okay, this is the another point. Now, the last but not the least, that is, electric field lines are perpendicular to an equipotential surface, and hence work done in moving a charge on an equipotential surface is 0. See, I have told you that electric field, see, electric field Electric field lines are perpendicular to an equipotential surface, and hence the work done in moving a charge on an equipotential surface is 0. In the previous property, I have told you that if the lines, whatever the lines passing through the equipotential surface are perpendicular, then the potential will be 0, because the dipole lies along the one direction and other two directions are negligible. Then that will be equal to 0. Then the equipotential surface with it is having the equipotential surface with the potential 0. So if the potential is 0, then the work done in moving such a charges on an equipotential surface is also 0. Am I right or not? So if the potential is 0, if the electric field lines are perpendicular to an equipotential surface, these are parallel planes. See, just a second. See, if the electric field lines are perpendicular to the equipotential surface, and the if the potential is 0, then the work done in moving such a charge on an equipotential is also 0. Do you agree or not? Yes. See, the electric field lines are perpendicular to an equipotential surface. The work done in moving a charge on an equipotential surface is also 0. These are all some of the properties related to your syllabus. One important thing that I want to tell you that uh, two equal charges repel each other and two unequal charges attract each other. Okay, this is the property of electric charge, right? So in that condition, how the electric potential will be applied? So forces of attraction between the two oppositely charged surfaces, like if you consider the spherical surfaces, suppose this is having some kind of negative charge and this is having some kind of positive charge. I have told you that two surfaces, there is some force of attraction between this. If the two charges are unequal, I mean if the two charges are different, So there is some kind of force of attraction between them. How the two charges will attract each other? Let us see. They are go on attracting each other. They will lie each other and they form a polarity like this. Okay. So these are all some of the properties equipotential surface. So let me revise it. So equipotential surface is the surface passing through the points at the same electric potential. So equipotential surfaces around a point charge are concentric spherical surfaces. Equipotential surfaces around a charged cylinder or the line of charges are concentric cylindrical surfaces. So whatever the surfaces you consider, the charge distribution will also be in the same shape. I mean same surface. So the line of charge are concentric cylindrical surfaces. Now, equipotential surfaces around a point charge are concentric spherical surfaces. So, equipotential surfaces around a charged cylinder or a line of charge are concentric cylindrical surfaces. So, equipotential surfaces due to a large charged plane are planes parallel to the surface. Now, for a uniform spherical distribution of charges, like if you consider spherical shell or a sphere, the equipotential outside the spheres are concentric spheres around the center of distribution of charges. So, all the lines in a plane passing through the center of the dipole and perpendicular to the axis of the dipole lie in the equipotential surface of a zero potential. So, if the dipole lies along the x-axis, the remaining two plane is an equipotential surface with the potential 0. So if the potential is 0, the electric field lines are perpendicular to an equipotential surface, and hence the work done in moving such a charge on an equipotential surface is also going to be 0. I hope this concept equipotential surface is clear to you. The next important and for most important concept, that is potential energy. It's a basic phenomenon. Okay, potential energy. What do you mean by potential energy? Okay, potential energy. The word itself indicates the amount of work done the amount of work done in bringing the system of charges from infinite to a given configuration electrostatic potential energy of a system of charges. See, potential energy, electrostatic potential energy of a system of charge is defined as the amount of work done, okay, the amount of work done in bringing the system of charges from infinite to a given configuration electrostatic given configuration, so electrostatic potential energy of a system of charges, so that electrostatic potential is called as potential energy of a system of charges. It's just like a bringing the system of charges from infinity to the given configuration of the state. Okay, given from infinity to the given electronic configuration, I mean given state of the system. Okay, so such a energy, okay, such a system of charges is called as electrostatic potential energy. So these are also some of the important equations. So let us derive one by one. Here we have considered two system of charges. Here we have considered two system of charges. Let me derive it one by one. Potential energy of a system of two charges. Okay. So electrostatic potential energy of a system of two charges. So let us consider electrostatic potential of a system of two charges. So consider a system of 2 point charges Q1 and Q2. So suppose if you consider the two charges Q1 and Q2 which are at infinite distances. Okay, which are at infinite distances. So now let the charges are bring to point B having a position vectors A and B. Suppose okay, let us consider a point A and point B. So consider a system of charges of 2 point charges Q1 and Q2 at infinitely at an infinite distance initially. So let the charges are bring to point A and B having the position vectors R1 bar and R2 bar. Okay, these are R1 and this is R2 bar position vectors. So it will be in the vector form R12. Am I right or not? R12. Now, first of all, let the work done be the let W1. Okay, W1 be the work done, amount of work done bringing Q1 charge from B to from B from infinity to a point A. So not work done, that is no electric field will be passed in the absence of electric field. Okay, in the absence of electric field, suppose if I want to bring this Q1 charge from infinity to a point A, infinity to a point A, then the work done, okay, in the absence of electric field, the no net work done will be takes place in the absence no that because of no electric field, then W1 becomes equal to 0. Now let W2 be the amount of work done bringing Q2 charge from infinity to a point B. So work is done against electric field produced by Q2 charge. Okay, that is see, suppose if I want to derive, if I want to bring this Q2 charge at a point B, there is some kind of electric field, then amount of work done in bringing the Q2 charge from infinity to a point B. So work is done against the electric field. There is some kind of potential. Okay, there is some kind of potential that is V is equal to W divided by Q, where W is equal to V into Q. Okay. V is equal to W divided by Q. Now, W2 can be written as, how? The W2 can be written as potential at a point B due to a charge Q1 charge. So, W2 will be 1 divided by 4 pi epsilon naught into Q1 into Q2 divided by R12. Okay, potential at a point B due to a Q1 charge. If you bring the charge Q2 from infinity to a point B, then the work done is against the electric field produced by Q charge, the Q2, Q2 charge, that is electric field is produced by Q1 charge, sorry, infinity to a point B. So the work done is against electric field that is produced by Q1 charge. So W2 will be becomes potential at a point B due to a charge Q1. Okay, then so W2 can be written as 1 by 4 pi epsilon naught into Q1 into Q2 divided by R12. So now the total work done for arranging the Q1 and Q2 charges at a point A and B can be written as, okay. Now the total work done in bringing the two charges at a point A and B. Those two charges are Q1 and Q2. So this is W1 and W2. Okay. This W can be written as what is W1? 0. A bit 0. And W2 is, it is there in the board. Okay, 1 by 4 pi epsilon naught into Q1 into Q2 divided by R12. Just a second. This is R12. So the total work done in bringing the two positive charges at infinity to a point A and B can be written as 1 divided by 4 pi epsilon naught into Q1 into Q2 divided by R12. This is the expression for total work done when bringing the 2 point charges at infinity towards the point A and B. So this work done is called electrostatic potential energy of system of two charges. This work done is called electrostatic potential energy of a system of two charges. Okay. So this one is I have derived. Total potential energy of a system of two charges is given by U is equal to 1 divided by, or W can also be written as U. Total work done in bringing the two positive charges, two charges at infinity towards the point A and B can be written as Q1 and Q2 divided by R12. And the potential energy of a system of three charges is given. Suppose uh, the potential energy of a system of three charges is given. Let us consider 3 point charges. Just a second. So this is A, this is B, and this is C. Okay. So the charge from infinity Q1, Q2, and Q3. Okay. So these charges, okay, the charge is the total work done in bringing these three charges towards the point A, B, C. So from A to B, that is R12. This is R12 bar. From A to C, that is R31 bar. From B to C, it is R23 bar. Now consider a system of 3 point charges Q1 and Q2 and Q3 initially at the infinite distance. So we have considered at infinite distance. So let the charge are brought to point A, B, C having their position vectors R1 bar, R2 bar and R3 bar respectively. So now let W1 be the amount of work done in bringing the charge Q1 from infinity to a point A. So there is no net electric field. So that's why no net electric field. That's why W1 becomes 0 at a point A. Now, let W2, okay, let W2 be the amount of work done. W2. W2 be the amount of work done in bringing the charge Q2 from infinity to a point B. So the work done is against to electric field produced by Q1 charge. Then W2 will becomes 1 divided by 4 pi epsilon naught into Q1 into Q2 divided by R12. Okay, R12. This is equation number 1. And now the potential at point B can be written as this thing. Now let WT3. Okay, W3 will be the amount of work done in bringing the Q3 charge from infinity to a point C against the electric field produced by Q1 and Q2. So W3 can be written as potential at a C due to a point Q and also due to a point Q3. See, there will be two conditions. Okay, in this W3, the potential at a C due to a Q1 charge. Okay, in these two conditions, if I want to bring this Q3 charge towards the point C, there will be some two conditions. What are those two conditions? See, the potential at a point C due to Q1 and potential at a C due to Q2. So there will be two conditions. I mean, two charges are present over there. So I need to take this form as potential at a point C due to Q1 as well as potential at C due to Q2. So the equation will be, point to be remember, the potential. If I want to bring the charge Q3 from infinity to a point C, there will be two conditions. That is potential at a C due to a point charge Q1 and potential at a C due to a point charge Q2. So W3 will become 1 divided by 4 pi epsilon naught into Q1 into Q3, of course, divided by R31 plus 1 divided by 4 pi epsilon naught into Q2 into Q3 divided by R23. Okay. This is equation number 2. So the total work done for arranging Q1, Q2 and Q3 can be written as, that is total work done in bringing those two charges will become W1 plus W2 plus W3. So substitute all the values, that will become W is equal to, what is W1? That is 0. So what is W2? That is 1 divided by 4 pi epsilon naught into Q1 into Q2 divided by R12. And what is W3? That is 1 divided by 4 pi epsilon naught into Q1 into Q3 divided by R31 plus 1 divided by 4 pi epsilon naught into Q2 into Q3 divided by R23. So this is equation number 4. Okay, this is equation number 4. Now if you resubstitute the values, the equation will become 1 by 4 pi epsilon naught is common over all the equations. Am I right or not? So the remaining terms inside the equation is Q1 into Q2 divided by R12 plus Q1 into Q3 divided by R31 plus Q2 into Q3 divided by R23. This is the equation for work done in bringing the 3-point charges from infinity to a point A, B, C. So this is a work done is called electrostatic potential of a system of 3-point charges. Okay. Equation for 3-point charges. Though, so the energy of a system of several point charges is given by in the if you consider the n number of charges, so the general equation will be U is equal to summation of I where I is not equal to j, then U into ij is equal to summation of I is not equal to j into 1 by 4 pi epsilon naught into qi into qj divided by r ij. This is the expression for energy of a system of several point charges is U. Okay, I hope these derivations are clear to you. Potential energy, what is the definition of potential energy? And potential energy of a system of two charges and potential energy of a system of three charges. Suppose if you go on substituting the number of charges, the general equation for energy of a system of several point charges is given by this thing. Okay. So, dear students, in today's session, we have considered some important categories, concepts, that is equipotential surfaces, what are the properties of equipotential surfaces, and also the potential energy. And what is the potential energy? The potential is system of 2-point charges, potential energy is energy of a system of 3-point charges. So, suppose if you go on substituting the number of charges in the potential energy, then that potential will be written in the general form like this. So I hope these concepts are clear to you. So next section, let us discuss whatever the syllabus is there for you. So dear students, by this I am going to wind up the session today. I hope it will be very helpful to you. So please don't forget to subscribe our channel and learn more. Thank you.